So in this video, we're going to be discussing the final multi-agent pattern, the router pattern, or the routing pattern. Now imagine you have a research coordinator. You have a research coordinator. Yeah. So this is our research coordinator. Research coordinator with a medium text. So we have our research coordinator. And we give our research coordinator a question. We give the research coordinator a question. So the research coordinator then takes that question, identifies which experts need to be consulted. Let's say we need to consult an archaeologist. We also need to consult a geologist, and we also need to consult a meteorologist. All that topic has to do with fossils and stuff like that. Meteorologist. Yeah, I think I'm correct. Yeah, so we need to consult an archaeologist, a geologist, and a meteorologist. So the research coordinator identifies that. It breaks the tasks down based on what each expert needs to work on. It then sends tasks to each researcher in parallel. Then each researcher does their work, and all their findings is then synthesized into a final report. Probably they discover that, yeah, that bone belongs to an alien. Something of that sort. So they synthesize report. So they synthesize all that information into a report. This is how the routing pattern works. Yeah, that's the routing pattern. You can go home now. This is how the routing pattern works. The routing pattern is basically a multi-agent architecture where a classification step, not an agent, and this is very important, not an agent, a classification step analyzes the input. So we have an input here. We found some bones and we want to know what they're about. It analyzes the input. It then breaks it down into subtasks. Task 1, task 2, task 3. It breaks it down into subtasks. Or that's done here actually. It breaks it down into subtasks. It then identifies the agents that are to work on it and in parallel distributes that work to the agents. So take your part. So it breaks it down. This is the archaeologist's work. This is the geologist's work. This is the meteorologist's work. So give the archaeologist's work to the archaeologist, give the geologist's work to the geologist, and give the meteorologist's work to the meteorologist. So it dispatches these tasks to specialized agents in parallel. Everyone works on it, and the system synthesizes the final report into a unified response. It synthesizes all the results into a final response. This is how the routing pattern works. It is optimized for queries that benefit from consulting multiple knowledge sources simultaneously. That's your use case right there. Any situation that benefits from consulting multiple knowledge sources simultaneously, running multiple tasks simultaneously, the routing pattern fits perfectly. The routing pattern is designed to work in parallel. So if you just have one shot stuff, don't bring it there. If your stuff are going to be one shot, you only need to consult one agent, do something in sequence. No, that's not what we're doing here. We don't do that here. Parallel work is the main selling point and strong point for the routing pattern. For example, let's say you bring a paper or you bring a question, not a paper, that asks, what are the economic, environmental, and social impacts of electric vehicles? The research coordinator is going to analyze that and break it down into 3 parts. 1 to economics, 1 to environmental science, 1 to sociology. All of them work in parallel. It will then synthesize all the results and provide the final report. So based on your question, is broken down. It can be broken down into 4 parts. It can be broken down into 5 parts. It can be broken down into 7 parts. And specialized agents are going to be spun up simultaneously to work on them and to give you a final synthesized result. The key insight here is parallel dispatch to specialists synthesis of results. Keep that in mind. Parallel, dispatch to specialist, and synthesis of result. Now let us look at some characteristics of this design pattern. We come here, and I think I should be able to stick the characteristics around here. Let's do our asterisk characteristics, asterisk and obelix. So characteristics. First, it always has a classification step first. So it always runs a classification step first. Not a classification agent, a classification step. So you have a classification step. This is where the router is going to analyze and decompose your query so that I can identify the different parts and the different agents that are to work on it. Also, like I said, it is heavily, fully and permanently designed for parallel execution. Multiple agents get to work simultaneously. They get to work in parallel. And also, each agent receives a targeted piece of the puzzle. Targeted in the sense that it is according to their specialty. Each agent gets a domain-specific query. So the classification step is going to do the breakdown and package a very detailed instruction, domain-specific to a particular specialist agent. So it's going to package that. It can be for 3 agents, it can be for 2 agents, it can be for 5 agents, depending on the number of specialists it has identified to work on that particular task. Next, we have selective routing. Now, for example, these are not the only experts that the research coordinator would have in the department. These are not the only experts. There can also be a paleontologist. There can also be a biological scientist. There can even be someone that specializes in metal works. But based on the task it was given and the breakdown it did, it would only call the guys that should be involved. It will only invoke relevant agents. So even if you have like 15 agents in this system, only the relevant ones are going to be called. Only the ones that are relevant to the task at hand are going to be called. It's also similar to the sub-agents where you only call the agents that you need, but these ones will always operate in parallel, unlike in sub-agents that you can actually have them working sequentially. Also, we have result synthesis. Result synthesis. There is a synthesization step. I hope I'm calling that correctly. Synthesization. Okay? There's a synthesis step. So that's where all the results are combined into one unified response. So every result from all the sub-agents is collated, and that response is handed over to the user. Now, this is also done statelessly. So the operation is typically stateless. The agents only receive what they need, and each of the requests is going to be handled independently. No context from any other guy. The archaeologist is going to do his work, walled away from the geologist, who is also separated away from the meteorologist, and definitely the archaeologist too. Everybody gets to do their own work independently. Then the system, the harness, is going to synthesize everything and pass the final result. And you may have guessed, there's definitely context isolation with that. So context isolation is also one of the characteristics of this pattern. So classification first, there's always a classification step first. Parallel execution, the execution is always parallel. It's always if you are doing one short stuff, don't come here. It's always parallel. We need to spin up 2, 3, 4, 5 agents. Then the subtasks are targeted at the specialists. Selected routing, or selective routing, rather, not selected routing, sorry about that. So there's selective routing. So we only select guys that we need. We don't need everybody. We only select guys that we need. Result synthesis, that's the final step before a response then goes to the user. Then it's typically stateless, walled gardens, silos of operation, then context isolation. The context of each agent is isolated from each other. So yeah, those are the characteristics of this design pattern. Now, we've definitely seen how this kind of pattern works when we're looking at workflows, in LangGraph. The routing workflow, the router workflow kind of works similarly to this. But let me just show you how the fan-out process looks like. That's the process of sending different tasks to different agents. So let us go to pseudocoder. And let's say after the classification step, we get something like this. We get this variable, classification, which is a list. Classification. Oh, yeah. So we get this variable, which is a list. And inside, we get dictionaries of each classification. And what this will typically be is that we'll have, let's say, a variable called source. Source is going to be the name of the agent that is going to take it up. Let's say we have archaeologist here. Now I'm wondering why I picked this very complex names. So archaeologist, then we have query. We have query. That's the instruction that is to go to them. So this will just be a bunch of blah, 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 blah. So let me just do that. So we have that. You can name this agent, you can name this source, whatever. Source is just trying to depict the fact that you are probably doing a research that involves you querying different sources. So this is geologist, has his own query, and we have meteorologist, and he has his own query. So this is the result of your classification step. This is what you save in state, a list of how the task has been broken down into the sources to query and what we're going to be querying. So with this information, you can then add a routing function to your graph. You can add a routing function to your graph using send. This is where send is the main player, is the star of the show. You add a routing function using send, and what send is going to do is that it's going to get that particular classification from state. It's going to get that classification from state. It's going to loop over it, and for each of them, it's going to send, or it's going to return a send object. It's going to return a send object, which the agent is going to be the source, and the query is going to be classification query. Yeah, that's going to be the state for that node. So, or that agent. So it would pick the agent or the node and then send the context here, picking it from this breakdown that I just did. And when you want to do the synthesis, you can always use a state variable that has a reducer. For example, let's say results. Let's say you have results in state, and this can basically be an annotated state channel, which is a dictionary or a list, which is a list, and you can use the add function from operator. Use the add function from operator. Oh, this is very, very important. Else, each result is going to override the previous one. Each result is going to override the previous one. So you want to make sure that you have this with the right reducer. Am I doing this right? I think it's this. Yeah. So you make sure that you add the data type. This is going to be a list, and we're going to be adding to the list. So we add all the results, and then you can then process the results yourself. You can take the result state variable, and you can loop over it to generate your final result. Here you do the classification step, you do the fan out step using send, and then you synthesize by making sure that each agent is sending their results to this results variable that you have added a reducer, an additive reducer to. So yeah, that's how you ensure that your results are collated. Now let's go back. An important thing to discuss, because it will most likely be a question that has been going across your mind as we're working on this, or rather as we're discussing this pattern, which is how is it really different from sub-agents? How is it really different from sub-agents? So let us dedicate this section of the video to router versus sub-agents. Router versus sub-agents. Let's dedicate this section to router versus sub-agents. And let's see how they compare. The first heading we're going to be discussing this under is routing decision. How they make routing decisions. Let me see if I can have some sort of tabular stuff here. So this will be router, and here we have sub-agents. Router and sub-agents. So first is routing. How do they make routing decisions? Routing decision. Let's be explicit. Routing decision. A router makes his routing decision through classification, through a classification step. That's how a router makes his routing decision. By the way, I think I need a line. I think this would, yeah, let's do this. Some lines here. Let's put another one here. Yeah, that's good. So, a router makes his routing decision through a classification step. So it's a very structured step, and it produces a structured output. However, the supervisor does dynamic reasoning. Dynamic reasoning. So the supervisor is the one that uses an LLM to determine what he should call, when he should call it, how he should call it. Should he call something in parallel? then one order later. The reasoning is dynamic. So that's why they are added as tools, because LLMs can better handle tools. So a router's routing is structured. Use a classification step, breaks it down into a bounded list of actions, whereas the routing for subagents is dynamic. The next is when routing happens. When does the routing happen? When does the routing happen? For the router, the routing is always once and upfront. It only routes once. It does its classification step, determines where it should go, routes, and is done. It's not going back and forth, it's not coming back. It's going to route in parallel once, synthesize the result, and everything is done. Upfront and once. But that of sub-agent goes on continuously. And even during... No, that's not right. It goes on continuously during the conversation. Yeah. That of sub-agent goes on continuously during the conversation. So it keeps getting context back from results of previous routing decisions and determining whether it's to make another routing decision or to return the final answer and stuff like that. So everything is dynamic. Next is parallelism. In the router pattern, parallelism is native. Parallelism is the native execution. Like I told you, don't use router if you don't have parallel operations to run. Don't go there. So it's native, that's the native execution. For subagents, it's possible, but supervisor controlled. It's controlled by the supervisor. It's possible, but the supervisor gets to control when it is done. So it's a runtime decision. Also, how does multi-turn happen? In a router, multi-turn is stateless. So it's typically stateless. You just run a single request through, it breaks it down, runs it in parallel, and that's done. The execution step is not trying to get feedback and decide on what next to do. So other information is not necessary. Whereas in subagents, you need that state to operate. So this is naturally stateful. Of course, you can always add a checkpointer to your router and run it on several turns, but it's just good for running parallel tasks straight up and getting your results back. So that's how multi-turn happens. So what about subtasks or sub-questions? In a router, this is generated by the classifier. So the classifier already generates everything that is needed, any follow-up questions, any 1A, 1B, all those kind of multi-level querying. Meanwhile, in subagents, this is generated by the supervisor on demand. So the whole dynamic thing is still going on. Next, how is synthesis done? How are the results collated? Since both of them are going to be working with multiple agents, how is the entire result going to be collated? For a router, there's a dedicated synthesis step. As we have seen. However, for subagents, the supervisor synthesizes. For subagents. Next, how about complexity? And you have guessed this. In my opinion, this is more structured. Not my opinion, actually. It's the way it is. It's more structured and explicit. So we can say that it is less complex. Whereas once you start dealing with flexibility and dynamism, which is very, very good, things get more complex. So I believe subagents can really get complex with time, especially when it comes to debugging and tracing and all that. Now, what is this best for? What are they best for? Router is best for situations where you have known verticals. For example, like a parallel research. Let's go a step down. This is the last point anyway. Then subagent is better for dynamic routing and a conversation scenario. Like I said in the subagents video, I'm planning to create a course where we get to build ChatGPT from scratch with all its basic features. And I feel that sub-agents is going to be the best for that. It can hold the conversation and can call multiple agents on the ground to perform more specialized tasks. So yeah, these are your differences. These are your differences between the router design pattern and the sub-agents pattern. This is your wall of decision, your decision framework. And I hope this finally answers any question around the differences between the router pattern and the sub-agents pattern. Now let us take a look at benefits and trade-offs. Benefits and trade-offs. The benefits on this side, back to writing benefits. And and trade-offs. Get rid of this out of here. So benefits and trade-offs of the router pattern. First super obvious benefit is parallel execution. Parallel execution is native to this design pattern. So once you have a system that requires parallel execution specifically, this is a strong pattern to consider. So parallel execution, which provides significant latency reduction compared to sequential flows. Next, when you have targeted queries, when your queries are defined and targeted, you want to consider the routing pattern. If it's a system where you know that out of the whole task, each agent is going to get an optimized sub-question, just go with router. Go with the routing pattern. Next is selective routing. So a bunch of the characteristics are basically their advantages. Only relevant agents are invoked. Also, there's clean separation. Context doesn't leak into one another. Each agent gets to do their work without being bothered by others' operation. Also, it is scalable. Yeah, it is scalable. You can keep adding specialists and it knows when to call which, and it calls them in parallel, making it very, very efficient. So vertical agents just working on their specializations. Also, it's predictable. It's quite predictable. I think of all the design patterns, it is the most predictable. Very predictable. You know the steps, you know the decisions it will make, you know how it will make them, you know how it will finish off. So it's just awesome. And the more predictability, the easier things are to debug. You have explicit routing logic, straightforward when it comes to debugging. Also, cost control. Cost control is another strong benefit. You know which agents will run, you know how they will run, so you can kind of estimate what they will consume in terms of tokens. So that would help you because when each agent runs, you can even do things like configuring the model, max tokens. So based on how elaborate you want the work to be, for example, in research, which is one of the strong use cases, if you want the research to be very, very elaborate, you want to allow it to use as much tokens as possible. But if it's just going to be like compact information that you want to get from each research by each agent, you can set a max tokens. You know, don't use more than 5,000 tokens. Just use more than 5,000 tokens. And you can do that because you know that you can still get enough information to produce a reasonable final result. But if you limit tokens when you're using sub-agents, it might cut off their decision making, it might cut off their flow, and it will just truncate the entire process. So here you have more grip on the cost. Now let's look at trade-offs. First, it is stateless by default. So each independent work is independent. You will need extra work for multi-turn conversations. So I wouldn't advise them for multi-turn conversations, but if you need to, you will have to do more work with checkpointers and feeding back states to every single agent and bundling it up with the classification step and all that. So that can introduce some extra complexity. Also, there's the classification overhead. So you have to actually call an LLM at that point. Yeah, you have to call an LLM to actually help you break that down. The predictability can also become quite rigid. So it can't dynamically make decisions. The decisions don't go further than just breaking things down and picking the agents to work on it. There's no dynamism mid-execution. It can't adjust its flow. It's just, say, here's go, and it goes. So you can't make edits or have some sort of intelligent rerouting. So that's one more thing. Also, the quality of the synthesis. you have to provide a strong synthesis prompt to make sure that it is synthesizing correctly. If you provide weak instructions, it's just going to give you a very subpar report or result. So you have to make sure that you explicitly detail how you want the response to be presented. Another thing is that there is no agent interaction. Yeah. It is one of the few systems that the agents don't collaborate in any form of way. Even sub-agents, they, in a way, collaborate through the main agent. They can feed off each other's context. But here, nothing like that. The agents don't interact at all. Agents can't consult each other. You have to be refeeding context if need be. And that is not even the best use case for it. So you might want to pick a different pattern at that point. Also, query decomposition. This is similar to synthesis quality. If you don't provide good instructions on how the classifier should split the query, you are going to be splitting wrong, delegating wrong, and at the end of the day, it's going to be garbage in, garbage out. So your eventual response or results is not going to be good enough. And it can even be almost useless. So you want to make sure that you write proper prompts for your classifier so that the model can properly classify your task. So those are our benefits and trade-offs. And if you have been following, you know it is time. If you have been following from other videos, you know it is time for use cases. It's time for use cases. So we reduce these guys and talk use cases. What are the use cases for the routing pattern? The first one is, may have guessed it, multi-source knowledge. Multi-source knowledge operations. So you need to pull knowledge across different sources, search across different sources in parallel. The sources can be documents, they can be websites, they can be discussion boards, they can be from code. Yes, this pattern can help you excellently. Another use case is research queries, which is the example that we have been riding on throughout this video. Research queries. So you consult multiple databases, multiple information banks for research purposes. Also, if you want to compare, if you have comparison questions, who is better, Ronaldo or Messi? So you spin different agents, one with good knowledge of Ronaldo, one with good knowledge of Messi. They start collating stats. They start going through their football history, fitness, decision making, even soft skills like how they interact with their players, their coach, and everything, and then bring together a full comparison between Ronaldo and Messi. So if you have comparison questions, you need to compare two things. It's very perfect. It's very perfect for that use case. Also, aggregation. Aggregation queries. If you just want to pull, let's say, you want to do a research and say, what are the top 5 agentic tools? What are the top 5 agentic tools? So you can go out, do that research, and then synthesize and give you the top 5 agentic tools. You can also use it for opinion gathering. What do news websites say about the COVID vaccine? To go out, pull information from different news websites, and give you different opinions from different sources and how they compare. Also, it is very good for operating RAG pipelines. So if you have RAG with multiple retrievers, if you have a RAG system with multiple retrievers, you can perform agentic RAG, multiple retrievers, can perform agentic RAG and have this pull from a database, pull from different vector stores for different types of content. You can just pull from different sources and collate them into a single context. So that's another thing that you can use this for. Also, API aggregation. API aggregation, you can use it to call multiple APIs in parallel and synthesize their results. Most of these things will be done through APIs anyway. So this is more like a foundational use case that kind of covers a lot of these other guys, especially the first 4. Yeah, all these things will be done through APIs. So any type of API aggregation you want to do, this design pattern, which is a routing pattern, can help you with that. And that's the routing pattern.